All right, good day, everyone. Today we're going to be talking about our lesson 8-1, which is going to be function composition. Okay. Basically, the whole idea is we want to be able to determine the composition of two functions. What does that really mean? What does it really represent? And be able to solve out a couple different problems using this information. Okay. So let's go ahead and get right into it. So first off, in this situation, we have a hiker who is last seen at a visitor center at a national park and has been reported missing. The search and rescue team estimates that the hiker would have been walking at a rate of 2 miles per hour. The STAR team needs to determine the possible search area to look for the hiker. So let's get some context to this problem. So basically, you have this lost hiker that was last seen in a singular location. Okay? So what the search and rescue team is doing is basically saying he travels at 2 miles an hour, but he could be anywhere in a circular area of this position. Okay? Because they're basically assuming he's going to walk in a straight line and get to that point. Well, with this information, we can already understand and already take into account that we already know that at some point we're going to have to try to figure out the area of the circle that he traveled, and then we can use that to help simplify the actual area of his search. Okay, we don't want to expand out this circle too far. For example, if this is where he was at, we don't want the circle to be giant and we're wasting our time searching. Okay, we want to be as efficient as possible to help find this guy. Okay, so what we're going to do is we're going to build two equations, as you kind of can see below. The first one is the theoretical search area of a circle, okay? Which, if you notice, I've done right here, okay? F of x equals pi x squared, which, if you think about the area of a circle, it's just pi r squared, correct? So the first equation here, we're building the area of a circle, where x is going to be your actual radius, okay? Now, the radius is going to be also in miles, which is going to be an important idea here, okay? In the second equation, we're going to create one based off the miles per hour, which is pretty straightforward, okay? We can create g of x equals 2x, and in this case, our x value is going to be the actual hours that you traveled, okay? And so what we need to be able to do is we need to be able to start to simplify these ideas. We got to start taking what we have here and build off of that, okay? Here's kind of the main thing you want to think about. In each of these examples, they are related in some way. G of x is the miles per hour, so how fast he can actually walk. F of x is the radius per miles, and that gives us the actual answer itself is going to be the actual search area, so the area of the circle. Well, these separate don't really help me out, but combine them together using composition, I can actually create a singular equation that can help me out a lot. Here's how this works. We're going to use a function composition, which is basically this notation right here. Basically stating that if I plug the g function into the f function, or even write it like this, I can create a singular equation using two different examples, okay? So what I did here is I basically took the g of x, which is 2x, plugged it into my f of x equation to get a final answer of 4 pi x squared. Now, understanding the context of this is going to be very important. In number 4 here, they ask, what is the input of the composition? Well, now the input is hours. X is the actual amount of hours he is gone, or how long it actually takes him walking right now, okay? While the output is going to be the total distance traveled in the circle. So we're going to put in the time he's been missing, and we're comparing it to the total distance, which makes sense if we go back to the beginning here. If I were to combine these two equations, I would plug in hours to get the area of this problem. Okay, so see how I can take two examples that are similar, combine them to get a single equation that's related in everything? So that is a kind of first important step. Now, in this problem, number 6, just because it's something we've been discussing, it asks, what is a reasonable domain of the situation? Well, yesterday we talked about how we really want to focus on like square roots and 1 divided by x situations for domain restrictions, but there is another one that it's out there, but it's only in particular situations. In this example, we're dealing with a word problem. So x is meaningful. X is dealing with time. And so when I set a domain restriction, x has to be greater than 0 because time cannot be negative, okay? If he's lost all day, he didn't travel -4 hours, that'd be impossible, okay? That means he's time traveling. So understand that's what we're looking at right now. So when it comes to the domain question, the other third case where we might have a restriction is in a word problem where the X actually has meaning, okay? But this is the idea of function composition. We're going to be able to take two separate functions, combine them to get one meaningful function that represents multiple things. Now, in today's lesson, we're going to be talking about many different ways you can handle this, because if you remember last year in Algebra 2, we've actually seen these problems, but now we're going to go a little bit more complex with them, okay? So let's go ahead and continue on then. So the next thing we're going to talk about is what happens to a graph in a function composition. And so right now, what they want you to do in this problem, if we were in class, I would have you graph all these in the calculator and see, like, if you had separate, what do they look like, and then together, what do they look like. Obviously, with time purposes and the fact that these are all online lessons, I don't want to really take the time to do that, but I do want to kind of explain how this works. So I want you to think about if g of x was the absolute value of x, which in turn, if you think about it, any negative value is going to become positive. And if I were to plug it into this value, what's going to actually happen with the graph? Well, if I think about this, f of x to the x cubed is going to look like the graph to its right, where all my negative numbers are going to stay negative, all my positive are going to stay positive. But if you think about it, if I were to change it to this, or if I were to plug my g of x in, well, then all these negative values are just going to flip and become the positive values now. Okay? So see, notice how the absolute value of x cubed almost turns into like a quadratic function. Okay, just because it flips that only side. It's not going to affect the positive side, but it will affect the negative side. So these are important problems to really think about when we're actually dealing with this. It's important thing to think about as we're doing these problems. And how does the composition affect my graph? Well, we can clearly see here that if I were to change an x to an absolute value of x, well, then all negative values would become positive. So in two different examples here, I just kind of want to talk about how does this relate. So one of the examples they could give you is a graph like this. Let's say this is the original. Okay. Well, if this is the original graph, these are my original functions. So this is basically, I believe this is just f of x. Okay, this is the original, this is f of x. Well, they want to actually explain, like, how is this going to change based on the different types of composition? So the first one here is g of f of x. And notice how they make g of x the absolute value of x. So this one's going to turn into y equals the absolute value of f of x. And the thing I want you to think about is how that equation is written. Okay? This type of a problem is going to only affect the actual answer. Okay? Notice how the graph changes. This one's actually going to affect the answer of the problem. Notice how in the original, you have a negative value here. Well, in the new one, it flips and becomes a positive value. Because if I had the absolute value of f of x, all my answers would just become positive. The number I'm plugging in is not going to change. The answer for f of x is not going to change. It's just the final output. We're basically saying whatever answer we get here, take into the absolute value. Okay? And that makes sense throughout the whole graph. Notice how literally at that point, everything's flipped. Okay? Everything from 1 here, everything from the point of 1 gets flipped on my new function to where if I had all this negative space, it now becomes a positive space. Okay? The next one I want you to think about is what happens if I switch it? What happens if I take g of x and put it as the inside as the function that's getting inputted? Well, in that case, I would have to think of this as f of absolute value of x. Okay? And so the thing I want you to think about now is that I'm not really affecting the actual answer itself. I'm actually changing how this graph looks. Now, we know how an absolute value function looks. Okay, what I'm basically doing is I'm creating an absolute value function with preset results. Well, notice down here how this portion matches this portion up here. The only time it changes is in blue here, where this becomes the same portion. And the reason it does that is pretty straightforward. Okay, if you think about an absolute value function, don't you think about how it's a V-shaped figure, how it matches on each side? That even though we have two different lines here, technically this line is a comparison of this line. Well, that's the same thing that's happening here. The positive and the negative regions, because no matter what, it becomes a positive, should match. So in this case, notice how both of these regions, we have our negative values being inputted and our positive values being inputted match, because it's following the idea that now I'm inputting an absolute value. Okay, so it's trying to understand, like, how does it actually affect your graph? In this one, if it's the outside value, it's going to affect your answer, like in letter A here. It affects your answer and flipping it. In the second one, it actually affects your x value and how your original graph is set up. Okay? And that's just one of the things I want you to think about as you're working through this, as you're seeing these problems, that how does the function composition affect your actual graph? Now, the last type of problem is actually just working backwards, okay? Now, obviously, you're going to have problems where you have to actually do function composition, where you have to plug those values in. But you've seen those. You've done those. You probably feel pretty confident about it, or I hope you do, okay? And if not, we can still go through those problems because those are fairly easy. The last type of problem that we're going to see is how do we actually adjust an equation that's already given to us and they want the actual original function? So, for example, if I see letter A here, which is h of x equals 1/2 x minus 5. And I want to basically understand that h of x is f of g of x. But what I want to know is what is f of x and what is g of x. Well, to do this, I have to try to think back to like the original. How could I plug in one equation to get another? Well, in this problem, I want to think about, first off, what is the separate equation? Well, technically, this is separate of itself, okay? So what I can do in the g of x function is say that that was probably my original that I plugged in. While the f of x, I just want to think about how would I actually get that composition based off the original. Well, if I plugged in 1/2 of x, notice how I actually get to that position. To where if I actually took these two and did function composition, I would get back to this function here. So all I'm trying to do is trying to break down how would these look if I separate them into two separate functions. Okay, and you can always try to see like what is one function, what is another function. Okay, if I continue with another one of these, let's say we looked at letter B. Letter B is 1/x squared plus 3. Well, same thing. I want to look at this as two separate functions. Think about how you have this whole thing on the bottom of that problem. So I can pretty much assume that g of x has to be that value that's sitting on the bottom there. While f of x, the value that was the original that I plugged the g of x into, probably is this 1/x. Let's look at one more tough one too. Letter D basically has us do x squared plus 6x plus 9. So we have letter D, which is x squared plus 6x plus 9. Now, originally looking at this, this is tough, right? It's very hard to try to think about how can I actually factor this, or how can I actually simplify this? Well, the trick to this one is actually factoring it out. If I factor this out, the one thing I'll notice is that both 3 and 3 in my x method will work. So technically this is x plus 3 times x plus 3. Or in other words, I can simplify that into x plus 3 squared. So you notice how based on simplifying that, I can turn what I have in the original into a factored form. Well, now if I'm looking at this, I can say, okay, well, these are my two values. The g of x value is my x plus 3, and my f of x has to be x squared. And just like that, I've come up with the two separate factors, the two separate functions that I need to have based on factoring out that equation. Okay. That was kind of the whole idea of today's lesson. Now, there's a lot of different information there, but it's really just trying to understand composition and how I can take two separate functions, combine them to create a new function, okay? But using logic, I can either work backwards, I can change the graph, I can always think about ways like, how did this affect this based on the originals, okay? Thanks for watching. I will see you all in class tomorrow. Have a great day.